I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a few numericals based on a fringe width. Before doing the numericals, let us try to understand the concept of fringes and fringe width. So let us see this diagram. So in which we are going to understand how fringes are formed, and this experiment is given by the scientist Young. So it is named after the scientist Young as Young's double slit experiment because we are going to consider two slits here. We are calling it as Young's double slit experiment. So what do we have here is a source. This is a source S. We consider a monochromatic source. This is a monochromatic source. So what do we understand by monochromatic? Mono means single, chromatic means color. So light of single color, or it is single wavelength. So we are considering light of single wavelength. So the light that is coming from the source is emitted in all directions. So we consider the light that is falling on these slits. Now, these two slits are placed equidistant from S, means the distance it travels from S to this slit and from here to here is the same. Then what happens, because they are equidistant from here, these two sources will become coherent sources. They are coherent sources, means they are in phase. Since the distance travelled by the light from the source S to these two slits is the same, these two slits will act as coherent sources. Now, the distance between these two slits is considered as small d. Small d is the distance between the two slits. Now, the light that reaches this slit, as we have seen in Huygens principle, each point on this will act as a secondary source and sends out secondary wavelets. So these are the waves that are coming from the slit, first slit, and we also have waves coming from the second slit. These are the waves coming from the second slit. Now these waves coming from these two slits, when they superimpose on each other, depending upon how they arrive, if they travel the same distance, means if the path traveled by these waves is the same, then they arrive in phase. Means all those points will correspond to constructive interference, which gives rise to a bright fringe. So these waves will superimpose, and when they superimpose, if they are in phase, means crest falls on crest, or if a trough falls on a trough, all those points will correspond to constructive interference. So we have constructive interference. And whenever we have constructive interference, the point gives rise to a bright fringe. That is what we call it as bright fringe or bright band. This is a bright fringe or a bright band. Now, upon superimposition, if a crest falls on a trough, when you have a crest which falls on a trough, so it gives rise to destructive interference. We call it as destructive interference. And because of destructive interference, we will get a dark fringe or a dark band. So this is the background we need to understand. Also, we have the conditions which we have already discussed in the theory. When the path difference is an integral multiple of lambda, we have constructive interference. And when the path difference is an odd multiple of lambda, half multiple of lambda, then we get a destructive interference. So these two are conditions for constructive and destructive. So what we observe here is now the point at the center, because these waves travel equal distance, travel same path to reach the point here, they will arrive in phase. So the central fringe is always a bright fringe. So this, whatever you see in yellow, is the bright fringe. Now on either side of the bright fringe, in interference pattern, you will have dark fringes. So this is the dark one. This is a dark band. So this is a bright band or a bright fringe. This is a dark fringe. Okay. Now if you see, these bright fringes and dark fringes, they alternate each other. Means after dark, you have bright, dark, bright, and so on. Even on both the sides. If this is the central one, on either side of the bright fringe, you will have alternate dark and bright fringes. Now, if you have to number them, if m is equal to 0 is the central bright fringe, m is equal to +1, +2, because we are taking in the upward direction. M is equal to -1, -2, because we are going in the downward direction. And if you see for dark band, if this is m is equal to 0, this is +1, +2, this is -1 and -2 you will have. So what we are trying to observe here is, because of the superposition of waves that are coming from these two slits, what we see on the screen, this is the screen, which is placed at a distance of capital D from the two slits. So here, lambda is the wavelength of the light we are using. Small d is the distance between the two slits. And capital D is the distance between the slits and the screen. Now, because of this, we are having alternate bright and dark bands. And we are calling them as fringes. So what you are seeing here are fringes, alternate bright and dark fringes. In our interference patterns, the interesting thing here is all these bands are of equal width. If you see, this is the width of the bright band. This gives us the width of the dark band. This is for the bright, this is for the dark. If you see here in the diagram also, the width of these fringes is the same. Now we are going to see the expression for these fringe width, and we are going to do some numericals based on this fringe width. So fringe width or bandwidth is what? First, let us try to understand the definition. Distance between any two consecutive dark or bright bands is called the bandwidth or the fringe width. Because we have named the topic as fringe width, otherwise both mean the same. The distance between the n+1th and the nth order consecutive bright fringes from O is given by xn+1 minus xn. So xn+1 is the distance of the n+1th bright fringe from the central fringe, and xn is the distance of the nth bright fringe from the central fringe. So if we want to find the bandwidth, we do xn minus 1 minus xn. So we substitute in the formula and we get beta is equal to capital D by small d into lambda. So this is the formula we are going to use. Now let us have a quick recap of what we are going to use throughout our numericals. So we are doing numericals only on fringe width today. We may be taking the Young's double slit experiment or the bi-prism experiment, but we will calculate the fringe width. So fringe width is denoted by beta. And the wavelength Wavelength of the light source is denoted by lambda. Now, distance between the two slits. The two slits are placed or separated by a distance small d, and distance between slits and the screen. Slits and screen is capital D. So if we have to write the expression for beta, beta is equal to lambda d upon small d. Beta is the fringe width. How do we get the fringe width? Fringe width depends upon the wavelength. It depends upon the wavelength lambda. Capital D, which is the distance between the slits and the screen, and also small d, that is the distance between the two slits. So if the distance between the two slits increases, the bandwidth decreases. If the distance between the two slits decreases, the bandwidth increases. So what we need to understand? So beta is directly proportional to lambda. So if lambda increases, the bandwidth increases. And if d increases, then also the bandwidth increases. But if the distance between the slits increases, the bandwidth decreases. And the converse is also true. Means if lambda decreases, beta decreases. If capital D decreases, beta decreases. If small d decreases, the fringe width increases. That is what we are trying to understand. And now in our numericals, what we are going to do is, if you are given beta, the fringe width, capital D, the distance between the slit and the screen, and small d, distance between the two slits, we can easily calculate lambda from here. So lambda is equal to beta d upon capital D. So we'll use this formula directly from here. Or sometimes we may be asked to calculate capital D, at what distance the screen has to be placed in order to get fringes of so and so size. Then we'll use the formula capital D is equal to beta D upon lambda. Simple. Only from the main formula we are writing. So capital D is equal to beta D upon lambda. This is another formula. And sometimes we may be asked to calculate the distance or the separation between the two slits. So small d will be equal to lambda d upon beta. So upon doing these numericals, our concept of fringe width becomes very clear. Means we'll try to understand how wavelength or the distance between the slit and the screen or the separation between them plays a very important role in getting the interference pattern. Now coming to the first numerical. Two slits are separated by a distance of 0.2 millimeter and they are illuminated by a monochromatic light of wavelength 550 nanometer. Calculate the fringe width on a screen at a distance of 1 meter from the slits. So whenever we get a numerical, the first thing we have to do is write the data given. What is the data given and what we have to find? So first given is two slits are separated by a distance of 0.2 mm. So always the distance here, separation between the slits is given by small d is equal to 0.2 millimeter. And we are taking a monochromatic light of wavelength lambda is equal to 550 nanometer. First we'll write the data and then we'll think about the conversions. And calculate the fringe width on a screen at a distance of 1 meter. So the screen is kept at a distance of 1 meter. Capital D. This is denoted by capital D. What we have to find is the fringe width beta. So what is given, what we have to find. So the next thing is which formula we are going to use. So what is the formula we will use? Beta is equal to lambda d by small d. Now if you see, we have these quantities in different units. No, it is of course in the same system, but the unit is different. So we will always try to use the SI system. So in SI system, the distances are measured in meters. So we will convert everything into meters. So 0.2 millimeter will be equal to 0.2 into 10 power minus 3 meters. This is the conversion. 1 millimeter is equal to 10 power minus 3 meter. Then we have the wavelength in nanometer. 1 nanometer is equal to 10 power minus 9 meter. All these conversions you need to remember. So 1 nanometer, nano means 10 power minus 9. So this will be 550 into 10 power minus 9 meter. And this is in meters, so there is no need to convert. So we have got small d, lambda and capital D. Now the next step is to substitute. We need to do the substitute. We always do the numerical in 4 steps. First is identify the data given, what is given, what we have to find, and use the appropriate formula. Then substitute, simplify, get the answer and express it along with the units. So when we substitute here for lambda, 550 into 10 power minus 9 into capital D is 1 meter divided by small d is 0.2 into 10 power minus 3. So what we get here is 2.75 into 10 power minus 3 meter. So the fringe width is given by 2.75 into 10 power minus 3 meter. You can use a calci. You can also write it as 550. You can write it as by 2 into 10 power minus 9. This is minus 3. If it goes up, it becomes plus 3. So we get minus 6. So 550 by 2, we can write it as 2750 into 10 power minus 6. So when you change that, as you shift the decimal places, you can write it as 2.750 into 10 power minus 3. This is in meter because we have converted everything into meter. And 10 power minus 3 meter is nothing but 1 millimeter. So I'll write it as 2.75 millimeter. So you can directly use your calculator and get the answer. But if you have to simplify, you need to know the conversions and how you simplify it. So the fringe width is given by 2.75 millimeter. Now coming to the second one, 2 coherent sources of monochromatic light of wavelength 6000 angstrom unit. Wavelength is given in angstrom. They produce an interference pattern on a screen kept at a distance of, the screen is kept at a distance of 1 meter. And the distance between 2 consecutive bright fringes. So here they are giving the distance between 2 bright fringes is 1.5 millimeter. You have to find the distance between the 2 coherent sources. So let us write the data. What is given? Once we write the data, the problem becomes very clear. So lambda is given. Lambda is equal to 6000 angstrom. And the screen is kept at a distance of 1 meter. So distance between the screen and the slit, we are taking it as capital D. So this is 1 meter. And the distance between 2 cones, we have seen in the theory, distance between any 2 bright fringes or dark fringes is the same and they are equidistant. So here we are writing beta is equal to 1.5 millimeter. What we have to find is the distance between two coherent sources, that is lambda. So what is the formula we are going to use? So for clarity or for you to remember, it is always good that we remember the basic formula for fringe width. Beta is equal to lambda d by d. But we have to find d. So from here I'll simply deduce or write the formula for small d. So small d will be equal to lambda d by beta. Instead of remembering 3-4 formulae, you can simply remember one basic formula for fringe width, and from that you can write any formula which is required depending upon what is asked in the numerical. So d is equal to lambda d by beta. Now let us look at the units. So wavelength is given in angstrom, and in SI unit it has to be expressed in meter. So 1 angstrom is equal to 10 power minus 10 meter. So we will write this as 6000 into 10 power minus 10 meter. D is given in meter. The fringe width beta is in millimeter. So we will write it as 1.5 into 10 power minus 3 meters. This we have already discussed. 1 millimeter. Milli means 10 power minus 3. So this is 10 power minus 3 meter. So let us substitute the things in this formula. The third step is substitution. So how do we substitute? Lambda is 6000 into 10 power minus 10 into d is 1 upon beta is 1.5 into 10 power minus 3. So we can simply write this as 6000 divided by 1.5 into 10 power minus 3, if it comes up plus 3. So it will be minus 7. So 6000 by 1.5 will be 4000 into 10 power minus 7. So we can also write it as 0.4. I'm shifting the decimal places 4. So it will be into 10 power minus 3 meter, or simply 0.4 millimeter. So what we are trying to find here is the distance, small d. The slits are separated by a distance of 0.4 millimeter. Now the third one. Light of wavelength 500 nanometer forms an interference pattern on a screen at a distance of 2 meters from the slit. If 100 fringes are formed within a distance of 5 centimeters on the screen, find the distance between the slits. So let us write the data. Wavelength is given lambda 500 nanometer. The screen is kept at a distance of 2 meters. So capital D. Distance between the slit and the screen is capital D. It is 2 meters. Now 100 fringes are formed within a distance of 5 centimeters. When we are talking about the fringe width, the width of each fringe we were talking about. Now the fringe width is not given directly. What is given here is for fringes, 100 fringes within a distance of 5 centimeters. So we have to find the width of each fringe and then find the distance between the slits. So we have to find small d. Okay. So in order to do the numerical, first we'll try to find beta. So if you are having 100 fringes in 5 centimeters, what will be the width of one fringes? So it will be 5 by 100. See, this is centimeter. I can write it in millimeter also, 50 by 100. So this will be 0.5 millimeter. So this gives us beta, the fringe width. We are having 100 fringes in 5 centimeters or 100 in 50 millimeter. So 50 by 100 will give us 0.5 millimeter, or we should write it as 0.5 into 10 power minus 3 meter will be the meter. And lambda is again given in nanometer. So we will write it in meter. 1 nanometer is 10 power minus 9 meter. So 500 into 10 power minus 9 meter. Now write the formula for D. Beta is equal to lambda D by D. So small d will be equal to lambda D by beta. So lambda is 500 into 10 power minus 9. D here is 2. And beta, the fringe width we got as 0.5 into 10 power minus 3. So we'll write 0.5 into 10 power minus 3. So we can simply write it as 1000 into 10 power minus 9 divided by 0.5 into 10 power minus 3. So this gives us 4 into 10 power minus 3 meters. We can write it in millimeters. So 4 millimeters. Directly you can express it in millimeters also. Now coming to the fourth one. Two coherent sources of monochromatic light of wavelength 6000 angstrom unit produce an interference pattern on a screen kept at a distance of 1 meter from them. The distance between two consecutive bright fringes is 0.5 mm. Find the distance between the two coherent sources. So it is a similar kind of problem. Only thing is we'll try to understand if the distance varies, how the fringe width varies. So write the data. Lambda is 6000 angstrom. Capital D is 1 meter. Distance between consecutive bright fringes, that is beta, is 0.5 millimeter. And we have to find small d. Distance between the two coherent sources. Now which formula we are going to use? I'll again write the basic formula first. Beta is equal to lambda d by d. So which gives us small d is equal to lambda d by beta. So next step is conversions. So 1 angstrom is 10 power minus 10 meter. 1 millimeter is 10 power minus 3 meter. So this is 10 power minus 3 meter. So once we got lambda, d and beta, we are going to substitute. So 6000 into 10 power minus 10 into 1 upon 0.5 into 10 power minus. So 6000 by 0.5 will give us 12,000 into 10 power minus 10 minus 3 if it goes up plus 3. So 10 power minus 7. So if I shift the decimal places, we can write it as 4 decimal places I have shifted. So 1.2 into 10 power minus 3 meter or 1.2 millimeter because 10 power 3 is milli. So the distance is 1.2 millimeter. Now, in Young's experiment, the distance between two slits is 0.8 mm and the distance of the screen from the slits is 1.2. The fringe width is 0.75. Calculate the wavelength of light. So the first time we are going to calculate the wavelength. Till now we have been calculating either the fringe width or the distance between the slits. So now we are going to calculate the wavelength. So we'll write the data first. Distance between the slits small d is 0.8 millimeter And capital D, distance of the screen from the slate is 1.2 meter. And the fringe width beta is 0.75 millimeter. We have to find lambda. So we have the formula beta is equal to lambda d upon small d. This implies lambda will be equal to beta d upon capital D. So let us look at the conversions now. This is in millimeter. Let us convert it into meter. 0.8 into 10 power minus 3 meter. This is in meter. This is again in millimeter. So 0.75 into 10 power minus 3 meter. So once we get the values of small d and beta, we will substitute in this and get the wavelength. So beta is 0.75 into 10 power minus 3. Small d is 0.8 into 10 power minus 3 upon capital D is 1.2. So when you simplify 0.78 into 0.8 upon 1.2, you get 0.5 into 10 power minus 6. So here you have minus 3 and minus 3. So this is minus 6. Now I will shift this decimal to 4 places. So I can write it as 5, 1, 2, 3. So I can write it as 10 power minus 10 meter. And 10 power minus 10 meter is 1 angstroms, because generally we express the wavelength in angstroms. So it is 5000 angstrom. So the wavelength of light that we are using here is 5000 angstrom. So thank you. For more numericals, you can refer to Engineering Physics by Gaur and Gupta or Cengage Publications, Engineering Physics by Cengage Publications. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.